This is lecture 19, homogeneous linear system. The idea of this lecture is to solve for the solutions of a homogeneous linear system analytically. As you remember, we tried to solve for the second order differential equation last week, right? And we learned that we have three types of solution. We have distinct roots, you have repeated roots, and you have convex roots. The same idea can be transformed into system of differential equations, right? And when solving the homogeneous linear system of differential equations, you have three different types of solutions. And because we have a system of differential equations, we can turn that into a matrix vector form, as we did in lecture 17. And when we try to solve something in linear algebra, or we try to turn the system of differential equation into the matrix vector form, we try to solve it under the idea of eigenvalues and eigenvectors. When you solve for eigenvalues, there are three different types of eigenvalues. That is really distinct real eigenvalues, you have repeated eigenvalues, and you have complex eigenvalues. So in a way, the eigenvalues and eigenvectors are just, or eigenvalues basically, just some solutions that you can solve for the system of differential equations. And the eigenvalues or the corresponding eigenvalues for you to actually, so you solve eigenvectors to give you some guidance on how the solution is going to behave, right, given different initial conditions. All right. So that's kind of the introductions to the homogeneous linear system. Go back to the example that we see in lecture 17, that you can find the solutions of the system, of this linear system right here. Right. And the two solutions are 1, -1 times e to the -2t, and 3, 5 times e to the 16. We got two solutions. And in lecture 17, we show that these two solutions are linearly independent, or they form a fundamental set of solutions. And therefore, you can write the general solutions for the system as the linear combinations of x1 and x2, as described right here. Right? Given that c1 and c2 are some arbitrary constant. And because of the form that we have when we get the solutions are in exponential form. So x1 is 1 -1 times e to the -2t, that's exponential form, or exponential function form. And this is 3, 5 times e to the 16, that again is the exponential function form. And because of all of this example, right, if you look more into this type of example, you will see that the solution vectors, in this case, x1 and x2, have the form of k1, k2 times lambda t, right? So for k1 and k2 are some constant, and again, lambda, you have lambda 1 and lambda 2 in this case. So lambda 1 is equal to -2, and lambda 2 is equal to +6. These are just constant, right? So k1, k2, lambda 1, lambda 2 are constant. Right. So that is, as we prompted to ask, whether we can always find solutions of the form for the general homogeneous linear system. Right. So the solutions are going to look like this: x equal to k1, k2, up to kn times e to the lambda t. Again, right, the case you're having here are constant. Lambda is the value that we need to look for. And foreshadowing, lambda in this case called the eigenvalue of the system. For this column vector, right, the column of k1, k2 up to kn, I'm going to call that the eigenvector. Right? And I'm going to use the vector v in this case, e to the lambda t. And we found that the solutions probably look like this form. You have the eigenvectors multiplied with exponential functions raised to some eigenvalues times the independent variable. Okay, and this is the kind of the solution, or the general form of solutions for the homogeneous system of the form x equal to a times x. So where a is an n by n coefficient matrix. Now I'm going to name this formula star. So if star, equation star, is to be a solution vector of the homogeneous linear system, again, of the form x equal to, so sorry, this is x prime, it's equal to a times x, then what you have is, instead of only x on the right-hand side, what you do is that you're going to take the derivative on both sides of this particular equations right here. Then take the derivative on both sides of star. We have that x prime equal to v times lambda times e to the lambda t. So now we substitute what we know into the system. So x prime is of this form. X is this solution right here. Then we have, so the system becomes Right, we start out with a homogeneous system of this form, x prime equal to a times x, but x prime is equal to this. It's going to be equal to v times lambda times e to the lambda t equal to a times x, but x is equal to this. So a times x, but x is equal to b times e to the lambda t. So we're going to manipulate these new equations we just got. Right? So we put everything on one side. You cannot just delete e to the lambda t at this point. Later on, of course, we can, but I just want to put everything on one side of the equation first and then delete e to the lambda t later. So it's going to be a v times e to the lambda t minus v times lambda times e to the lambda t equal to 0. Now, e to the lambda t is a common factor, and v is a common factor as well. Right? Remember, lambda is a constant, e to the lambda t is also a constant. So therefore, when you take out the v and the e to the lambda t, this is what I have. Right? Because v is on the right-hand side of the matrix A, so therefore, when you bring it out or when you factor the vector v, it has to stay on the right of A. And capital I here is the identity matrix. Okay, now you can delete e to the lambda t on both sides of the equations, right? And you get that a minus lambda I times v equal to 0. Sorry, this is a 0 vector. So the system becomes, let me organize things a little bit here. So this equations, I call the equation 2 star. So we say that the matrix equations 2 star is equivalent to the algebraic equations. So that is, you have A11 minus lambda times K1 plus A12 times K2, so on and so forth, up to A1n times Kn equal to 0. And then you have A21 times K1 plus A22 minus lambda times K2, so on and so forth, up to A2n times K sub n equal to 0. And we do this for n equations. So you have an1 times k1 plus an2 times k2 up to ann minus lambda times kn equal. And to find the solution of the algebraic system of equations, we must find a non-trivial vector v that satisfies this equation a minus lambda I times v equals to 0. To do so, we solve the following characteristic equations. That is to find the determinant of a minus lambda I equal to 0, or to stand for the determinant of a minus lambda I. And when you solve for this a minus lambda I, that is called the characteristic. That's going to be a polynomial equation, right? And the values that you got, lambda, the value lambda that you got is called the eigenvalue, right? And the corresponding vector from the eigenvalue is called the eigenvector. So the solutions of the characteristic equations. Lambda is called an eigenvalue, and the corresponding vector v is called eigenvector. So again, to get the solution to the system of differential equations, what you do is you're going to solve the characteristic equation, which is the determinant of a minus lambda I equal to 0. You solve that particular equation, you get some value. The value is going to be lambda, and it is called the eigenvalue. And we use this eigenvalue to find the value of, or the representations of vector v, and that vector v is called the eigenvector. Okay. Now, again, as I mentioned before, there are 3 different types of eigenvalues: distinct real eigenvalues, repeated eigenvalues, and complex eigenvalues.